Okay, in this video we're going to talk about the last of the new things in the Laplace transform. Um, the, so I'm thinking that we have already talked about new functions, right? The Heaviside function, the Dirac function, and today we're going to be talking about a new operation. A new operation, and the operation takes in two functions of time and produces a function of time, however we define this, and this is going to be called the convolution of f and g. Okay, now this definition is kind of interesting. That's defined to be the integral from 0 to t of f of u, let's make sure that's clear, f of u times g of t minus u du. And so a couple things to notice here, right, is that the variable of integration is here, and this t appears here and here, right? That's the same t. Okay, and so when the u is integrated out, right, you're going to end up with a function of t. Okay, now why would we want to do something like this? As it turns out, we're looking for a way of, so is there an easy formula for inverting a product like f of s times g of s? Right? Unfortunately, we know that the Laplace transform of the product of f of t times g of t is not equal to the product of the transforms, and that's fairly easy to show. You could basically pick any two functions of t and that'll probably not work. Okay, so as it turns out, it is the convolution that will give you the product. That is, and this is actually something called the convolution theorem. The convolution theorem says that if I take the Laplace transform of f of t convolved with g of t, I can find that by taking just the Laplace transform of f of s and multiply that times the Laplace transform of g of s. Okay, or similarly, you could say that the convolution, right, is equal to the inverse Laplace transform of the product. Good. All right. Now we are not going to prove this. It's proved in other places. We will, for the next 7 minutes or so, just talk about how the convolution is going to be computed. It's hard to get a good intuition about the convolution, although there is some intuition. In fact, the convolution is being used right now in lots of different places, and in fact it created a big boom. The convolution is used heavily now in something called neural networks. And in fact, we're using what's called the one-dimensional convolution. That is, our functions only have one variable. But if we went into the two-dimensional convolution, we could take the convolution of images, and actually that's where the neural networks comes in. The neural networks processing likes to use the convolution, and there's some really interesting things happening with that. So if you're actually looking for a senior project, we might just do it specifically on the convolution. But like I said, for us right now, we want to focus mainly just on how to compute the convolution and how to use the convolution theorem. Okay, so let's do a couple of computations real quick just to see how to compute the convolution. So for example, how would I compute, let's say, the convolution of the function 1 with the function t. Okay, by definition, that's equal to the integral from 0 to t of f of u, and so in this case it's just 1 times t minus u, so that's just going to be t minus u du. Okay, so that's going to be, now I'm integrating with respect to u, right? So that's just going to be t u minus 1/2 u squared from 0 to t. Right, so that's t squared minus 1/2 t squared minus 0. So it looks like 1/2 t squared. Good. So notice in particular that 1 convolved with f of t is not necessarily f of t. Okay? In fact, 1 convolved with 1 is not equal to 1 either. You can compute that yourself. One property about the convolution that's not obvious, but is true by the convolution theorem, is that if you take, we'll just write it as a lemma, if I take f convolved with g, that's the same thing as taking g convolved with f. So on the one hand, right, if you're taking, it's not obvious if you're looking at the integral. We're going to look at the integral here just for a second here, just so we can show you. Okay, so these two integrals are going to be the same. Again, that's not obvious, but it is clear by the convolution theorem, right? Because if I take the Laplace transform of f convolved with g, that's f of s times g of s. That's the same thing as g of s times f of s. And so if you take the inverse Laplace transform, you get g convolved with f. So the two things are equal to each other. Very good. And so the upshot of that is that when you're trying to compute f convolved with g, you can decide which one you want to come first and which one you want to shift. Okay, so sometimes it's easier to shift one than the other. So let's do another example maybe. How would we take the I lost my place. The convolution of, how about t with sine of 2t? How would I take the convolution of t with sine of 2t? Well, one way is to actually just integrate it. And so let's do that. Now, which one do you want to shift is always the question. I think it would be a lot easier to shift the t than it is to shift the sine of 2t. So I'm going to put sine of 2u here, and then that's going to be times t minus u du. And the reason is because now we could integrate by parts sine of 2t, 2u, sorry. Now remember that sine of 2u. Good, now everything is in terms of u, so the t is constant here. So minus and then minus 1, and then cosine of 2u, that'll have to be a minus 1/2 there, right? And then plus 0, 1/4 sine of 2u. Good. Minus again. And so that's going to be equal to, here we go, minus 1/2 t minus u cosine of 2u plus, let's see, I've got 3 minuses, so minus 1/4 times the sine of 2u, and then we integrate from 0 to t. Good. So that's going to be minus 1/2 times 0 times cosine of 2t, right? Minus 1/4 sine of 2t. This whole thing minus, I'm running out of space and running out of time. Minus 1/2, and now 0 goes in for u, t cosine of 0, which is 1, and then minus 1/4 sine of 0, which is 0. Okay, so we end up with what? Minus 1/2 t minus 1/4 sine of 2t. Good. Now, just for fun, let's compute this a different way. We might go a little bit over time, but that's okay. Instead of doing this directly, I'm going to take the Laplace transform. And so I'm going to take the Laplace transform of t star sine 2t. And then so that's going to be 1 over s squared times 2 over s squared plus 4. Right? And so now I can rewrite that using partial fractions. Right? And so if we do that, we get that 2 is equal to a times s squared plus 4 plus b times s squared plus 4 plus cs plus d times s squared. A little bit of algebra here. As cubed plus 4as plus bs squared plus 4b plus, are you getting the idea that we're doing this a lot? Plus ds squared. Okay, yeah, we do that a lot. So now our s cubed terms, it looks like 0 is equal to a plus c, and then our s squared terms turn out to be b plus d, and then our s terms turn out to be 4a. Any other s terms? Oh, that's the only one. And then constants, 2 is equal to 4b. So therefore b is equal to 1/2, a is equal to 0, c must be 0 then, and then d is minus 1/2. Ah, good. So let's see if that makes sense now. Where am I? A is 0, so that term goes away. I'm left with b is 1/2 times 1 over s squared. My c is equal to 0, and so then I have minus 1/2 1 over s squared plus 4. Good, so that's going to be my 1/2 t minus 1/2, oops, 1/4, because I'm going to need a 2 there. And now I'll have a sine of 2t. Good. So what we had before, we seem to be off by a negative sign. You see where the negative sign, whoops, came from? Minus and a minus is a plus. There it is. Whoops, that should be a plus 1/2 t. Very good. So now we have double checked our answer even. And so there's the convolution, and there's the convolution, and hopefully they are the same. I think they are. I think they are. I think they are. I think they are. Good. Okay, it's getting late. Let's wrap this up. So this has been a discussion of the convolution and how to compute using the convolution, and actually how to compute using the convolution theorem. Okay, so when we get back, we'll the next video, we'll take a look at a few more examples. All right.